two Italians, Ubertino Battisti and Sandro Coriasco from Turin, and in part with Richard Nest. So let's see. What's the goal? The goal is to develop a calculus of Fourier integral operators for boundary value problems in the spirit of Boutin-Morval's calculus. So in case you don't know Boutin-Morval's calculus, don't panic. I'll say something about this in a few minutes. There's additional interest, and actually it came before from this, because there was the Atiyah-Weinstein index theorem for closed manifolds, and at one point it was actually Eric Leichnam who asked me, couldn't you do this for boundary value problems? And that was a long time ago, and it turned out it required a lot of machinery, and eventually this is what I'm going to speak about today. And there was additional interest in this because there's an old theorem by Atiyah-Singer which classifies the order-preserving isomorphisms of pseudo-differential operators. And when we started looking at this algebra, the question was, maybe this is the algebra classifying the isomorphisms of Boutin-Morval's calculus. And that seems to be the case, although it's not yet proven. Okay, so this was the goal. Let me start with this situation. So we have two manifolds with boundary, x and y, and we have symplectic morphisms on the cotangent bundle, which, as usual, is assumed to be one homogeneous in the fibers. So it's the standard setup, even though it's not quite standard, because now we have a manifold with boundary, and we want this symplectic morphism to preserve the boundary. Okay. Otherwise, you'd be in trouble. But that's a restriction, of course, for the symplectic morphism. Okay, let's come to the background. What are we dealing with? And I want to say a few words about this. So you probably all have encountered boundary value problems during your basic analysis courses or a course in PDE. And if you look at Boutin-Morval's calculus at first, it looks slightly strange. So Boutin-Morval says, well, I won't consider boundary value problems or inverses to boundary value problems. No, I do a calculus and basically a pseudo-differential version of boundary value problems. So everything you could, I mean, at that time when he did this, it was 71. So pseudo-differential operators had been extremely successful in analysis. You had all these tools. And we all know that this first proof of Atiyah-Singer wouldn't have worked without the use of pseudo-differential operators. So this was a strike to get a calculus. So what he did was the following. He said, I'm going to consider matrices, and these matrices have 5 entries. The first is a pseudo-differential operator. This is this P+. And there's right away a little problem because pseudo-differential operators are defined on open sets. So if you have a manifold with boundary, you have an open set. So there's a very brutal way of defining a pseudo-differential operator. You assume it's defined on a larger manifold. So you have a function which is defined on the half space or on this manifold with boundary. You just extend it by 0. It's maybe not the most subtle extension, but it is a simple extension, does the job. Then you apply a pseudo-differential operator and you restrict again. So you see already that there is some trouble that might arise here, and I'm going to say a little bit about this. So P has to satisfy the transmission condition. Okay, then there's strange objects like singular Green operators that you've heard of, but you don't know yet. There are trace operators that you all know from the theory of boundary value problems. There are potential or Poisson operators, which do precisely as you probably think they do. And then there's the one object you all know that's a pseudo-differential operator on the boundary. So basically, what's really clear up to now is this entry in the lower right corner, this S. And they act between sections on vector bundles over the manifold and over its boundary, just as in the usual case. So let me say, why is this good? One reason is it contains all the classical boundary value problems, because you can simply set this bundle F1 to 0, then K and S disappear. You take G equals 0. Yes, and P a differential operator and T a trace operator as for boundary value problems. So that's fine, fine situation. These are inside. Okay, what turns out is also the inverses to the classical boundary value problems, or more refined, the parametrices will be part of this. And now you also see how this G arises, because if you think of how you invert, say, the Dirichlet problem, then you know the first thing is you do is you take the Newton potential, and the Newton potential is nothing but the parametrics to the Laplacian. But then this won't solve the Dirichlet problem because you don't have taken into account the boundary problem. So if you want to use the Green's function, you have to make this additional change where you adapt the Green's function so that actually the boundary value is 0. That's this correction term that is usually hard to find, while the Newton potential is obvious. So this correction is this part G. And then K is the usual Poisson operator, which takes something at the boundary, maps it to something fulfilling the equation in the interior, and having the prescribed boundary value. So K is what you think it is. Okay, so this is just a very rough introduction. The point is, now you have matrices, you can compose these matrices, so assuming the vector bundles fit together, but that's clear. But once this is done, everything works out very nicely. As said before, we have this sort of non-subtle way of extending by 0. You know from pseudo-differential operators, they preserve smoothness. So if things were smooth up to the boundary, they're certainly smooth in the interior. Now you extend by 0, so the 0 part is also smooth. It's only at the boundary that something can arise, a singularity. And actually, this happens depending on the operator. And there's the transmission condition pointed out in Hermander's book saying, well, you need a special condition on the symbol of P so that it actually maps functions which are smooth up to the boundary to functions which are smooth up to the boundary. It is satisfied for differential operators because you all know you apply a differential operator, then you get the delta at the boundary. So once you restrict to an interior, the delta is gone, and the rest is smooth up to the boundary. So differential operators satisfy this. Their parametrices satisfy this closed under compositions, adjoints, and things like that. So what I should also mention is that ellipticity in Bedem-Walz algebra is characterized by 2 symbol levels, as you might know from boundary value problems. Classically, you have the interior ellipticity of the principal symbol, which in this case really is just the principal symbol of P. So it lives on the cotangent of the full manifold, and it's supposed to be invertible up to the boundary. That's, you all know from Laplacian, something like this. And then there is, in classical theory, the condition of Lopatinsky and Shapiro, which is an operator-valued symbol that lives on the boundary and sort of looks in the normal direction whether an operator on the line, on the half line, is invertible. And so this is the boundary principal symbol. I don't want to write it down because it takes a lot of space, but roughly if you have this idea, then this is good enough for the talk to follow. Okay, the Atiyah-Weinstein index theorem is what makes this thing really interesting. And to explain this, let me just do the following. So you have, now in this case, closed manifolds, X and Y. You have the simple ectomorphism, just the same as before, one homogeneous in the fiber. And then what you can do is you can associate a Fourier integral operator of order 0 with this simple ectomorphism. If you are a little bit familiar with the idea of Fourier integral operators, so a Fourier integral operator is basically described by its phase and an amplitude. So as an amplitude, you just pick a unitary section of the Maslov bundle, any, your favorite section. And you take, okay, this chi, this simple ectomorphism, defines a Lagrangian in between the cotangent bundles. So this Lagrangian, as you know from Hermander's theory, is locally described by a phase function. This is the phase function you take. So you take this phase function that characterizes your Lagrangian and an arbitrary section of this thing, and you get a Fredholm operator. Okay, I wrote f of chi. This is not really true because the thing might depend on your choice of the section. And the point is, it does not if the Maslov bundle is trivial or the dimension of the space is larger than 2. For a very simple reason, and I come to that at the end of the lecture. Okay, the Maslov bundle is a line bundle over the manifold, and it's basically described by e to the I pi over 4 times the Hessian matrix. No, not the Hessian matrix. The second derivatives with respect to theta of this phi. Okay, it's sort of a thing that can basically take 4 different values, and sort of as you go around. Okay, that would take more time to do this. It's a line bundle, just locally numbered. Okay, why was this interesting? And there was a good thing Weinstein showed in connection with this, which is not quite obvious, but in this case not so difficult. You assume that you have Laplacians on the 2 manifolds, say they're Riemannian, and say you choose the metric in such a way that the principal symbols of the Laplacians, so basically the metric tensors, are given by composition. By composition with chi. So chi is our symplectic dimorphism. It maps sort of one principal symbol to the other, and then it turns out, if you look at the sequences of eigenvalues, so the eigenvalues, you have a second order operator, so the eigenvalues grow like j to the 2 over n. So both sequences go to infinity, but if you shift the second sequence by the index of this operator f, then this is bounded. It's very strange. So you can really say something about these 2 sequences.
Even true in the non-Kähler case, the no connection between the Riemannian and symplectic structure.
Well, here.
Okay.
That is strong. Yeah, otherwise could be true.
Is that implied if it's Kähler? You have that condition.
I don't think so, because you could have 2 completely different metrics. Basically you have 2 manifolds here, x and y, and this is a strong condition connecting the 2 metrics. Right? It says basically that the principal symbols are just a Gij. So the Gij are mapped via the chi one to the other. So actually basically have one Riemannian metric and the other one is given by this chi. But for the talk, I thought I should say, well, if you have a Laplacian, everybody's going to ask, how do you find the Laplacian on an arbitrary manifold? Okay. Does this answer your question? Okay, so computing the index of this operator f chi was an open problem for quite a while. There had been work by Seldich, by Gilliman and Boutet-Mauvel, and eventually this was proven. This was solved first by Epstein and Melrose in 1998 for the case where x and y is the same manifold, so basically for Fourier endomorphisms. And what they did is they reduced this to the computation of the index of a Dirac operator on a closed manifold and used the Atiyah-Singer index theorem. And there was a second solution given for the general case a little bit later by Leichner, Nest, and Zigan, who did this in the framework of deformation quantization, sort of in the spirit of the algebraic index theorems. Okay. The funny thing is, I have to admit this was my own fault. From all these papers, I mean, Epstein has a sequence of papers in the Annals of Mathematics, and talking to Richard, I had always assumed it was clear that all indices could arise. And people give you the impression that this is the case, but then if you try to nail them down, and one funder did that, it turns out that nobody really knows whether there is an operator which has non-zero index. Okay, still, in this in this case, this is still a good result because this means you don't shift the things, and you have the other result. So if all have index 0, this just means the sequences are anyway bounded. Okay, but it turns out, as I learned only a few months ago, you don't know. Okay, then let me speak a little bit about the theorem of Atiyah and Singer. Again, we have manifolds. They don't even need to be compact in their case. And you look at the algebras of scalar-valued classical pseudo-differential operators. And what they showed in 1976 was the following. They have a little topological condition, namely that the first cohomology class of S star x is 0. And then they consider an isomorphism which preserves the order. In a very simple thing, so it maps pseudo-differential operators to pseudo-differential operators. If one has order m, the image is also order m. Then it turns out there are not so many of those, namely, these isomorphisms are all given by conjugation with an invertible Fourier integral operator. It's not a very well-known theorem, and quite striking. The proof actually is sort of operator algebraic. You look at the characters of this thing, and then you understand what's going on. In this case, it's not such a difficult proof. It's maybe 5 pages, but you have to know what you're doing. Just recently, Atiyah and Merus wrote another paper on this thing, and claimed that the condition on the vanishing of the first cohomology class might be removed. But I only saw the preprint, and I didn't fully see how this was. Okay, it's probably true. Okay, there's one strange thing. Okay, so far the situation seems fairly natural. We have this symplectomorphism. It respects the boundary. But if you think of it little closer, then, okay, one thing you might know, does it really have to stop at the boundary? Can you extend it? It's not clear that you can extend it to the double. Actually, this is sort of unlikely. But in any case, you can extend it a little bit across the boundary. That's what you should call it. Moses' strict way you do it. Well, openness argument. Okay, that's probably what everybody believes. But there's a second thing, a strong implication of the fact that it preserves the boundary. The thing is, and that was something Merus observed in his paper from 1981, Fourier integral operators on manifolds with boundary. If you look at this symplectomorphism, then the fact that it preserves the boundary implies that it also induces a symplectomorphism of the cotangent bundles on the boundary, also one homogeneous in the fibers. And the thing is, this symplectomorphism actually extends to 0, basically because you have this one free variable which doesn't take part in the whole business, which can change. That's the main argument. And then it turns out that at the boundary, the symplectomorphism has to be trivial. So trivial in the sense of people from symplectic geometry, they call something trivial if it's not really a mixing of variables and covariables, but the symplectomorphism comes from a diffeomorphism of the boundaries, and then is lifted to the cotangent bundle by just taking in the cotangent bundle the adjoint of the differential to take care of the multiplication. So for Merus, this was actually the reason. So he proves this in the first, say, 10 pages of his papers. Not that he needed 10 pages for this, we need a page or 2. To introduce the B calculus, because then he has more freedom. But in our case, we really wanted to have precisely this situation. So this is something that's going to help us very much later. Okay, let me say a little bit about the technicality. So if if you're not into technicalities, you can doze off for 10 minutes, you won't miss much. Okay, or maybe you learn something about Fourier integral operators, which might also be nice. Okay, as I said before, we have the symplectomorphism chi, going from one cotangent bundle to the other. Then we look at the graph of it. The graph then is a subset of the Cartesian product of the two cotangent bundles. And for technical reasons, as always in this business, you change the sign of the second variable just to preserve the symplectic form. So this is nothing deep. This is just technicality. And usually they indicate this by having a prime that just convention. But if you do this, you get a Lagrangian in the Cartesian product. These Lagrangians are prescribed by a phase function. There's a basic theorem by Hermander saying once you have such a Lagrangian, you find a phase function which parametrizes it. But the first observation we have here is, we spoke about this Maslov bundle, that is crucial here. The Maslov bundle is trivial in the color neighborhood of the boundary of this thing. And that's due to the fact that the second derivatives of the phase with respect to the covariables just vanishes at the boundary. You see this for the tangential variables right away, because in the tangential variables, at the boundary, the symplectomorphism is a linear map. So you take two derivatives and it's gone. For the normal derivatives, it comes from the fact that it preserves the boundary, because the theta derivative of the phase is sort of the image of this xn, so this is preserved. And then also this is 0. And then you have always 0 in the second derivatives, so the bundle is trivial at the boundary. Okay, this has a nice consequence. It has the consequence that you can work a little bit easier with these operators, namely, usually you pick these phase functions parametrizing it, and this phase function you have to pick microlocally. So you localize not only in X, but also in the psi space, where you go to cones. So in this case, you can take the whole, you still have to localize the neighborhood of a point, X, but then you can take the whole cotangent bundle and write this thing, write the operator as an integral operator in this form. You have a kernel with a phase phi and an amplitude A, and oh god, this should, yeah. I changed twice from A to P, I'm sorry, at some place. There's probably something left. Okay, because P is better for the pseudo-differential part later. Okay. Okay, this is the good point. Okay, and okay, now if we want to define the Fourier integral operators in the interior, they're given locally. So in the interior, there's nothing we have to do. We have the standard theory given by Hermander and known since 30 years. So everybody knows this very well. It's only near the boundary that something happens. And near the boundary, it's harder to understand these operators. And just as in the case of Boucher and Mauvelle, we look at them as operator-valued symbols combined with this cut-off and extension procedure. So just to give a little of detail how this works, okay, you have the phase and the amplitude. You want them to satisfy the transmission condition, because otherwise it won't preserve smoothness. If you don't have this, it doesn't preserve smoothness. You write it as an operator-valued Fourier integral operator in the tangential directions. So in the tangential directions, nothing happens. It's only in the normal direction that something happens. And okay, let me describe this just a little bit. We have this phase phi describing it. As you know probably from classical Hermander theory, you can always split the variables x and y. So you have your phase basically concentrated on x, and the y part is just the usual multiplication by xi. Okay, chi preserves the boundary, so the derivative of this thing, this is basically the position of the image of xn, is, okay, xn equals 0 goes to xn equals 0 because the boundary is preserved. So this is constant 0. So the point is this does not depend on the variable xi n. So it's actually something that only depends on the variable x prime and xi prime. So this is the good point, because this shows you can separate the two directions in the Fourier integral operator. You have the tangential direction with the x prime and xi prime, and then you have the phase phi at the boundary, and you have the normal direction where you have the difference of the two phases, this one here, and you have the sort of a truncated one-dimensional Fourier integral operator, so you have e plus this extension by 0, the Fourier integral operator restriction, and it takes a function u and does basically the usual pseudo-differential thing. So you have the amplitude multiplies the Fourier transform of u extended by 0, and then you have e to the I, and the phase now is just the difference of these two phases that you have here. Okay, so this is the normal direction, and then in the tangential direction, you just have the remaining phase at the boundary. So this should be a y, because it's split up in the same way. Okay, and now because we think, we understand what happens in the tangential direction, we only have to focus on the one-dimensional normal direction. Okay, just to advertise this a little bit, because it plays a big role in the calculus of Boutet-Morel, and it helps if you understand these operators as operator values through the differential operators. And there's a very simple point. Probably most of you at one point have tried to use pseudo-differential operators, which are not scalar but take values in an infinite dimensional space. Finite dimensional space, of course, no problem. But then you should be careful. What you should use is you should use a group action on the space. And then instead of defining, the naive approach would say you take your operator, you take your symbol, you take the derivatives, and ask that the norm in LEF of this derivative satisfies the usual Hermander estimate. But this is not good. This usually leads you into trouble. What really helps, and that's the advertising point here, is to conjugate this with the group actions. So, and actually the group action with this eta inverse here and eta here, and then you ask that this is the case. Go home. If you're bored during the rest of the talk, just take sort of a second order operator and try it out. It really helps. Okay, and the question is, what do you use? And in the standard Sobolev spaces, you always use the dilation. So lambda is a positive number. Your group action dilates the function by this factor lambda, and in order to, this is just for convenience, to make it alto unitary, you add the square root of lambda so that it's a little bit nicer, but doesn't make a big difference for the estimates or so. This wouldn't change anything. Okay, so this really helps. If it's instructive to look at the example of a usual pseudo-differential symbol. Namely, suppose you have a symbol in n variables, and you split the last variable off. So you first fix, so you fix x prime and psi prime, and only look at the action in xn. So this is what I call op n of p, of course. So we fix x prime and psi prime, take the usual action in xn, and then this turns out to be a symbol of order m, operator valued, mapping from hs to hs minus m. Here you sort of see the strength, because usually if you have additional covariables and don't do the right thing, then you lose some information. Either it's very good if you're of order below 0, then it helps. But if you're order above 0, you get very bad estimates. Okay. but this was just a side remark. So this is here. If you expect the same to hold for Fourier integral operators, this is not true. But what you can show, and this is a little bit of work, is if you start with a symbol satisfying the transmission property, then you get an operator-valued symbol, but will not respect the Sobolev scale exactly. There's a little trouble with it. But it only maps in the sense that if I take a rapidly decreasing function, it goes to a rapidly decreasing function. So you have to slightly extend this from Banach spaces to Fourier spaces, but that's not such a big deal. What can happen is, basically, if you look at this, if no, let's skip this. Just it gets a little bit more complicated. And okay, once you have this, as I said before, once you know what happens in the normal direction, you take the usual Fourier integral picture in the tangential direction to define the operator. So we have our operator, which is now called pi with a chi for this symplectomorphism, extension restriction, as in the usual picture. And what you do is, okay, here in the tangential direction, you write the usual Fourier integral thing, and then in the normal direction, you have the operator you defined. Okay, even though in the normal direction as an operator-valued symbol, it doesn't behave as nice as you would expect it to be, still these operators map the Sobolev spaces in the right order. So whenever you have an operator of order m, then it maps hs of Rn plus to hs minus m of Rn plus. The usual restriction s has to be larger than 1/2. It's a little bit strange at the beginning, but this is this brutal thing of extending something by 0. The point is, of course, it's clear how to extend a C infinity function by 0, but it's not obvious how to extend a distribution by 0. So this only works, yeah, if you think of it. This only works if it's sufficiently large, and s larger minus 1/2 just says you can do it, and otherwise you're in trouble. Okay. Once you do this, things work actually fine. We have done now most of the work. It was hardest to define the pseudo-differential part, so the upper left corner of this thing. The p part is the difficult part. Everything else is fairly simple, and this has a very simple reason. Why is this simpler? The operators in Butel-Morat's calculus are given as operator-valued symbols, and they all, apart from the pseudo-differential part, they all have very good smoothing properties. So actually what this thing does in the normal direction, you don't care, because it's so smoothing, it could do anything, and it would still be okay. That's the philosophy behind it. So for example, if you look at a classical singular Green operator, a singular Green operator is an operator-valued symbol. So if it's order m, and I avoided this, the operators in Butel-Morat calculus have something called a class, but let's forget this for the moment. If you have class 0, then it's an operator-valued symbol mapping sort of temporary distributions on R plus. So this just means the dual space of the functions with a restrictions to R plus of rapidly decreasing function on R. This space to this space. Okay. So this is so nice. You can simply define the operator Fourier integral version of the singular Green operators just by taking this symbol and quantizing in the tangential direction with the symplectomorphism given at the boundary. And the same thing you can do for the other entries. So nothing happens here. Actually, this is just a standard Fourier integral operator then along the boundary as in the usual harmonic calculus. Okay. And then the operators look in this way. You see the matrix is basically the same as before. You have this sort of more complicated object, and the others just given by the quantization with this thing at the boundary, which is actually fairly simple, because at the boundary, this is just the lift of a diffeomorphism. Basically, it just means you have the standard operators pulled back under a change under the diffeomorphism of the boundaries. So these parts are very simple. Okay, the standard theorems hold. You have a composition of two of these operators, then let's call them A and B, then associated with symplectomorphisms chi and chi prime, then the composition is again a Fourier integral operator of this type. This requires actually quite a bit of work, because if you have these 5 entries in your matrix, it turns out you have to handle 13 compositions of operators. As in Bedem-Waals calculus, so this looks a bit strange at the beginning, the orders add up, so the order is just the sum of the orders, and the class behaves in a strange way, but that's the same thing in the non-Fourier integral operator case. So, okay, and if you look at the formal adjoints, you have to be a little bit careful with formal adjoints at Bedem-Waals calculus for a very simple reason. The reason is simply if you have if you have integration by parts, then you know that this is not true, but then you have to add the boundary values here. If you're on a manifold with boundary, right? If you have no boundary, this is fine. But if you really integrate, say, from 0 to 1, then this, and then you have to add, okay, f of 0 minus f of 1 here. So you don't have an adjoint already in this case we everything know. So first order operators or higher order operators usually don't have adjoints in the calculus. Okay, but if the order is 0 or less, huh? Okay, yeah. God. A very good point, yeah. Thanks. Okay, what is good about this? You get a Egorov type theorem. Egorov's theorem for integral operator says if you have a pseudo-differential operator and you conjugate it with Fourier integral operators, it stays a pseudo-differential operator. So this is also what happens here. Even if you have the boundary, so there's no perturbing effect here, you have an arbitrary Bedem-Waals operator, order m class d, and you conjugate with the Fourier integral operator, and here you have to be careful, the order of this operator should be 0 or less, because otherwise you have already trouble defining the adjoint, as I said before. But if you do this, then this conjugation is an operator of the same order and class. Okay, in the final time, I have to say something just a little bit about ellipticity. In the beginning, I told you that the ellipticity in Bedem-Waals calculus is characterized by 2 symbols, the principal interior symbol and the principal boundary symbol. Also, in this case, you can define 2 symbols, and they're a little bit nasty to explain. If you know Hermander's theory of Fourier integral operators, also already the principal symbol is no fun to explain. In our case, okay, the homogeneous interior principal symbol we define in the same way as Hermander, just by going to the pseudo-differential part and saying this is it. Because you know all the other operators do nothing in the interior. They're smoothing in the interior. You don't see anything. But then you can also define a homogeneous boundary symbol, which is a little bit simpler, but it's operator valued. So just as in the case of the usual operator, you have an operator valued boundary symbol, homogeneous on the cotangent bundle of the boundary. And in this case, it's a matrix of formed from the principal symbols of the entries here. Okay, and usually, as usual, ellipticity is just defined as the invertibility of both symbols. That's as in the standard case. Okay, The symbol maps you define, so they behave well under compositions and adjoints, so it makes sense to use them. And if you have an elliptic operator, then you can construct a parametrix. And once you have parametrics, just by the mapping properties, you see that the elliptic operators are Fredholm operators. Good, fairly clear. Okay. Now we thought it was easy to set up the Atiyah-Weinstein problem. It turned out to be more difficult than we thought. Okay, what you do is you take a unitary section of the Maslov bundle over our full manifold, and then we choose a Fourier integral operator with principal symbol u. That you can always do. That exists. So this is on these slightly larger manifolds x tilde and y tilde. And now you define your operator as, okay, you know the matrix can be very small. And in our case, it suffices to take a 1 by 1 matrix. Other bundles just 0. So we take this Fourier integral operator, cut it down with e plus and r plus, and take this e. And then you want to show that this is elliptic of order in class 0, and so a Fredholm operator. Of course, one thing is clear. By definition, we have the principal symbol of P to be U, and U is a unitary section. That's invertible. But to show that the boundary symbol of this thing is non-zero just took us a lot of time and was not at all obvious. So basically, well, I could explain this in private if somebody is interested, but it was much more difficult than I thought. Okay, but the good thing is, once you have this operator A, you can define the index associated with chi and u, the section u, as the index of this operator A that was constructed above. Okay, as in the standard case, it might depend on u. Okay, and as in your lecture you said, no lecture should be without a proof. Let's go to the proof of this. So it's actually a very simple lemma. Why is this independent of the choice of u? Okay. If the Maslov bundle is trivial, okay, if it's trivial, then you could just take, then, you just take 1 as the principal symbol, then you don't have much choice of a section in this thing. Okay. But suppose you have 2 unitary sections, u1 and u2, and you define the corresponding operators a1, a2, then the Egorov type theorem implies that if I take this, so I conjugate sort of the identity from the left and the right with these operators, then you get an operator in Boutet-Moval's calculus. But the principal symbol behaves well under conjugation, so the principal symbol is just the product of those 2 principal symbols. Now, if the dimension of x and y is at least 3, then the cotangent bundle has dimension 3, the cosphere has dimension 2, and then the sphere is simply connected. So once connected, so this is a complex valued function. So if the sphere is connected, just contract it to one point, the identity, and then you can deform the operator to the identity, and then you see that the index has to be 0, but the index is the sum of these 2 indices, and this is the index of the adjoint, so just the difference of the 2 indices, which is 0, so they coincide. Thanks. Yeah.
Related to
Yes.
How much this theory depends on this chi, and what depends only on this Lagrangian?
Okay. In this case, we start. Okay. A Fourier integral operator. You wanted actually to act between two manifolds, right? So locally, you have to have a Lagrangian in the cotangent bundle, and that's if you take the parameterization, that should give you a local symplectomorphic thing. It's not a symplectomorphism because you don't have the full manifold, but it preserves the symplectic structure. So yeah, for the general theory, if you just wanted to define Fourier integral operators, say on a small set, you don't need chi to be a symplectomorphism. That's removable. There you just need that locally this thing works out. Yeah. But of course, for the index problem, if you want to set up the index problem, it has to be defined on the full manifolds. Uh-huh.
Then it defines some Lagrangian relation.
Yeah.
Between cotangent bundles.
Mm-hmm.
And dimensions of the two manifolds need not be too easy.
Okay.
So that makes sense to think about some version for such Lagrangian relations between not equal dimensional.
I would think you run into trouble. But I'm not sure. I'd have to think about this.
Is the conclusion of the talk that the index chi is always 0?
No, it's not. It's
Your last, I already wondered why it's called a lemma.
no. Sorry. Maybe no. It's only the last lemma says. Let's go back to the. We can set up this index problem,
Yeah.
and you have two choices involved in this index problem. One is chi, but chi is your datum. And the second thing is the choice of a unitary section of the Maslow bundle. And of course, you don't really want to depend on this. So, and I'm saying whenever the dimension is at least 3, or the Maslow bundle is trivial, then it does not depend on this. Otherwise, say in the work of Leichner, Ness, and Sigan, they just prove a formula that depends on you. Okay. In this case here, we have sort of more questions than answers. Okay, even though everybody thinks, even in the classical case, all indices are right, nobody really knows, right?
Do you
And
have a single example now where the index is not 0?
nobody has. Okay, but I mean, okay, this sounds very stupid, but I only learned this when we were writing at the end the introduction of the paper, because I want to say, well, but this remains, and I only learned this when I really tried to nail down people. Saying, well, what? Okay.
So let's thank the speaker.
Thank you.
Anyone wants to make an announcement?
Very important. Peter arrives in 7 or 8 minutes.
But since we are at the end of the workshop, at the end of this semester, on behalf of all